Hello everyone, welcome back. So in this lecture we will be discussing the concept of KL divergence. So what is this KL divergence? So the KL divergence is basically used to measure how one probability distribution is different from another probability distribution. For example, if you have a probability distribution which is something like a Gaussian and the other one which is something like a uniform one, it will measure how much different is this probability distribution Px is from that of Qx. So by seeing this you can see that these two distributions are completely different. So KL divergence should give a very high value for this. But if the probability distribution is something similar to that of a Gaussian but it's slightly different like this, let us say it is nx, then if you want to calculate the KL divergence between Px and nx, it should give something close to 0, which signifies that these two are nearly similar but these two are totally different. So let's explore what is KL divergence and what is its possible application. So as discussed, this KL divergence is known as Kullback-Leibler divergence, and it's a measure of how one probability distribution is different from the second. For the discrete probability distributions, for example P and Q, the KL divergence between this P and Q is defined as this, and we denote KL divergence as D subscript KL with P / Q. So this is the basic nomenclature of defining the KL divergence, and mathematically it is represented like this: summation of all the values that the random variable capital X will take, then the probability of that random variable times the log of P divided by log of Q. So in short, it can be written in this form. So this is basically the definition for KL divergence. So let's take one small example in order to compute this quantity, that is the DKL. So the example is presented over here. So this is one of the probability distribution which we denote as by capital P. You can see that the random variable X having value of 0 has a probability of 0.36, random variable of value 1 has a probability of 0.48, and the random variable 2 will have a probability of 0.16. So this is for probability distribution capital P. For capital Q, it's a uniform distribution with probability of 1/3, which is actually 0.33. So all the random variables 0, 1, 2 will have a probability of 0.33. So it is also known as a uniform distribution PDF. So we want to compare these two PDFs, like how far they are from each other. So that is measured using the KL divergence as defined over here. So what we have to do is we have to just substitute appropriate values for this formula which is given over here. So you can see that one thing is important, and the important thing is which PDF you are putting on the first location and which PDF you are putting on the second location. So here I am putting Q on the first position. So as I am putting Q on the first position, this will be modified to Q of X log of Q of X divided by P of X. This is because you are using Q at the first location. So as a result of which, you can see that the very first value is the probability of the random variable X having the value 0, and that is 1/3. And this is Q of X at having the value of 0, and this is P of X having the value 0. Similarly, this is probability of Q having the value 1, and this is probability of Q having the value of 1, probability of X having the value of 1. So by merely substituting these values over here, you can calculate the KL divergence of these two probability distributions, and the value comes out to be 0.09637, and the units of this is nats. So you can see that the KL divergence is very small, and by inspection also you can observe that it's somewhat similar to uniform distribution but not exactly the same. That's why the KL divergence is coming as very small. So let's move forward. So these are the basic properties of KL divergence, which shows that the KL divergence between the two PDFs, that is P and Q or Q and P, will always be greater than 0. So this is very important property, and we will be using it while deriving the loss function of the variational autoencoders. The second property is that they are not symmetric. That is, if you take the KL divergence of P and Q or Q and P, it will not come out to be same. So that's why I specifically wrote this, because if I'll evaluate P with Q, it will not come out to be same. It will be different. But one thing is for sure, that the value will be less. So KL divergence doesn't have a symmetric property. So now once we have discussed these properties, now the next step is to generalize this to two different Gaussians. So let us say if we have two multivariate normal distributions defined as this and this, where Px is defined by a normal distribution n having a mean mu1 and covariance sigma 1, and Qx with having a mean of mu2 and sigma 2. So we want to derive a generalized expression for KL divergence for these two normal random variables px and qx. So we will calculate this generalized expression and let's see how we can do that. So let's recap our probability concepts. If we have a multivariate normal density, it is defined like this, as you can see over here, and please note that the dimension of this is k. That's why k is coming over here. Here x is the vector of length k cross 1, that is it has the elements x1, x2, dot 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 x of k. So x are basically the vectors over here. So that's why it's a multivariate normal density PDF. So if we have these two distributions as a multivariate normal density, then the KL divergence between these two normal distributions is actually defined like this. So this is basically a very important expression which will be used in our variational autoencoders. So I feel that everyone should know how to derive it. So in this tutorial, we will discuss the derivation for this so that you won't be feeling uncomfortable when I will be discussing variational autoencoders. So let's move forward and derive this. So as we know that the KL divergence between the two PDFs is given as this, which we have already discussed, and also we have discussed that the multivariate normal distribution is defined like this. And please note that here this is the determinant defined by double bars and it's not a absolute value. So if we take the log of this probability density function, then we will obtain this expression. You can do it, it's very easy. So you just take the log, you will obtain this expression. Similarly, if you take the log of the second probability density function, that is qx, which is defined here, so you will obtain the similar expression, but the covariance will be sigma 2 and the mean will be mu 2, whereas in the earlier case it is sigma 1 and mu 1. So next what we will do is we will rewrite equation 1 in terms of this expression, and it's very easy. And the thing is, what we are using is we are using an identity which is log a divided by b is log of a minus log of b. So using this you can write equation 1 as this, that is log of px minus log of qx. So now what you have to do is you have to substitute the values that we have derived in the earlier slide for log of px and log of qx over here, and then you will obtain this expression. So what you are doing is you are just substituting log of px and log of qx into this expression and you will get this expression as the result. So by observing this expression, what you can see is these two terms will cancel out. So they are not in the final expression, and we can club this and this expression together. And what we can write for this, we can write it like this: log 1 by 2 log of determinant of sigma 2 divided by determinant of sigma 1. Why I can write like this? Because of log a divided by b is log of a minus log of b. So I am using this identity and writing in this form. So this is the very first term that we are obtaining over here. Please mind that these are the determinants, and the second term I am writing as such, and this term is also I am writing as such. So the result is this expression. So this is similar to the earlier expression except these two terms, and we have modified this and this together to be written as 1 by 2 log of sigma 2 divided by sigma 1. So now the thing is how to solve these two expressions. So let's do one thing, let's take them one by one and solve it and see what we get. So let us focus on this term first. So we are writing it separately, and please note that this whole thing is multiplied by px, that's why px is coming over here. So we are summing up over all the values of the random variable having value x. So this in short can be written as this: E of p, that is expectation over the probability function p times the argument, which is this same one. Okay, so once we have written this, let's see how we can solve it further. So in order to solve this expression further, we have to know some identities from the linear algebra. So let's discuss that first. So one of the concept is trace and expectation trick. So by using these identities we can solve this expression. So trace is nothing but, if you have a square matrix, then the trace is basically the sum of all the diagonal elements that are present in this matrix. So it is very simple. So it's just a summation of diagonal elements of a matrix. So please note that here the argument should be scalar. So if x is a scalar, then expectation of x can be written again as expectation of trace of x. The other properties of trace are that trace of a times b is same as trace of b times a. The third property is trace of ABC is same as trace of BCA and CAB. Trace of ABC is not same as trace of ACB. This is very important, so you have to please note it. And expectation of the trace of X is the same as trace of expectation of X. So we can move out the trace and expectation interchangeably. If you note these 5 identities, then we can solve this problem. And there is one more identity, that is expectation of X transpose A times X can be written as expectation of the transpose of X transpose AX by using A. Because X transpose AX is normally scalar, so we can write like this, and then using the identity C we can write it like this, and using identity E we can write it like this. So you can check that all these 3 will be same with this. So once we have this in mind, so we can rewrite our expression, which is this one, as, so I am just rewriting it again, and you can see that it's a scalar quantity because it is matching this argument, which is X transpose AX, where A is actually sigma 1 inverse and X is X minus mu 1. So this is a scalar quantity. So what we are doing is we are interchanging the expectation and the trace. So what we are doing is we are using this identity and rewriting this expression as this. And next we will be using the identity that is in D to move this sigma 1 outside and bringing this X minus mu 1 to this side. So this is basically by making use of identity D. So now once this is done, what we can do now is we can use the identity E to move trace outside and expectation inside. So as a result, this expression results, and what you can observe is that this argument is basically a covariance matrix, and that can be represented using sigma 1, and this already we have as 1 by 2 sigma 1 inverse. So sigma 1 and sigma 1 inverse cancels out, results in an identity matrix of k dimension. So that's why trace of ik will come out, and the trace of ik is k itself, because any identity matrix having diagonal elements as 1 will result in summation of 1, and this summation is running up to k dimensions. So that's why the output will be k. So that's why we are getting as output k. So the simplified result for this expression is basically k. So once this is simplified to k, so now we will see how we can simplify this expression. So in order to do that, let's repeat this expression over here. So I have just repeated it again, with please note that I have kept the probability px also multiplied with this argument, which is important. So once this is written, so what we can do is we are applying a trick over here, that is we are adding and subtracting mu1 in this argument, that is this argument. So I am adding and subtracting mu1 over here, and similarly I am doing the same for this argument and repeating it over here. So once this is done, we will expand this expression, and the expansion will be, let us say x minus mu1 is represented by A and mu1 minus mu2 is represented by B. So it is A plus B transpose sigma 2 inverse, then you have is A plus B. So we are expanding this, and this is very easy, that is it is A transpose plus B transpose sigma 2 inverse A plus B. So you just expand this by multiplying the terms together, and you can note that there are 4 terms, and out of which 2 terms are same. So let's see what are these 4 terms. So first term, that is A transpose sigma 2 inverse A, will be given over here, and one of the terms is B transpose sigma 2 inverse B, that is represented over here, and the other 2 terms, which are B transpose sigma 2 inverse A and A transpose sigma 2 inverse B, are basically the same. So we are doing the twice addition of these 2 terms together over here. So once this is done, we obtain this expression. So let's rewrite this expression as expectation subscript P with the argument as this. So let's simplify these argument values and see what it will result. So what I have done is I have just repeated this same expression here, and we observed some interesting properties. And the very first interesting property that we observe over here is that the very first expression, that which we have written in terms of this pink line, is basically similar to the expression that we have already dealt earlier, with the difference. And the difference is that earlier we had sigma 1 inverse in between, but now it is sigma 2 inverse between. As you can check in our earlier expression over here, you can check that it is sigma 1 inverse in between, but in this case it is sigma 2 inverse. So in order to solve this expression, it is nearly the same derivation that we have to carry out as we have already done it in the earlier case with sigma 1 in between. So that's why I am writing it straight over here, with the difference that we have now sigma 2 inverse here, not the sigma 1 inverse which was in the earlier case. So you can do this exercise and you will obtain this expression. And the second thing that we note is that this expression is a constant. So expectation of a constant is always a constant. So this will result into a argument itself. And how about this expression? So this expression actually results in a value of 0. So we will see in the next slide how this 0 is coming. So this is basically the similar to earlier derivation, means that we have already carried out our earlier derivation. You can follow that, and with the difference that we have already discussed, that is, it has a sigma 2 inverse here. So for proving this as a 0, in the next slide we will discuss how it comes out to be 0. I am repeating this expression again. So as you can see, I can move the expectation inside. So what we obtain is the expectation of x, and expectation of mu1 is always a mu1, and expectation of mu1 and mu2 will always be a mu1 and mu2 because they are the constants. So once we move expectation inside the brackets, it will operate on x only. So the expectation of x is mu1. So this mu1 and mu1 cancels out. That's why the result comes out to be 0. So now the simplified expression is this for the second term. So once we substitute this and this into this expression, what we obtain is this. You can check by substituting, you will obtain this. So we have proved that the KL divergence for the two Gaussians, n1 having mu1 and sigma 1 as the mean and covariance, and qx having mu2 and sigma 2 as the mean and covariance, results in this expression. This is very important expression because it will be used in our interpretation of variational autoencoders. So thanks for watching my lecture. See you next time.